No, it's actually Derek Mansen. And we're going to be talking about geospatial indices, what they are, how we use them. So let's just start. A lot of this talk was adapted from a blog post by, let me see if I remember, Vladimir Agafonkin. Yes. At Mapbox. This post goes into a little more detail, so I'd recommend checking it out if you want to get some open source like JavaScript libraries that do these things and just explore some more. And like in the last talk, we're going to be talking about mostly things that apply to Vistar, but there are other approaches as well. Okay, so here's our first question. What is this? It's a data structure that's optimized for geospatial usage. Now, as an engineer, my first question is, do I have to do this? Can I not do it? That would be ideal. Can I use some other kind of data structure that I already know about? And the answer, unfortunately, is not really. Next slide. Yep. So the problem is, we're going to be looking at tree structures mostly, and trees generally require total ordering to maintain the balance property of the tree. So we can't really use a B+ tree because once you extend things to multi-dimensional space, you don't have that total ordering anymore. So we need to come up with something a little different. And something that's going to pop up repeatedly as we go over these is that we're going to use an approach called bound and branch, which is going to involve constructing our data structure in a way that allows us to cut off large parts of it as we are traversing it or searching for the answer to our query, so we can cut out a large portion of the search space as we go. So, some types of queries that we're going to be looking at. First one is a spatial range or radius, which is just asking, given a box or a circle, what objects do I know of that are within that area? Another type is the spatial point query. If it's sort of the inverse of the previous one, where at a given point I want to know all the objects that contain it. Another type is a spatial join. We're not really going to cover this today, but it's finding intersecting pairs of objects in our database. And the last one, and kind of the most complex and interesting, is nearest neighbor, which is, given a point, I want to know what the closest n objects are to that point, and that's going to come up a lot. So just to look at some concrete use cases, obviously we use maps a lot, and we're asking it like, I want to go to the restaurants near me. That's a type of nearest neighbor query. Another one is filtering, and that's a little more directly applicable to Vistar, where we're saying often, I want to run an ad campaign in New York, so I'd like to know where are all the screens in New York that I might show an ad on a map. And that's a spatial tree. And then finally, something that comes up here a lot is targeting. So the screen is requesting an ad, and they're saying, I'm at this point. Our ad server needs to know what shapes do we have in our database that contain that point, so that we can apply the targeting. We don't want to display an ad on a screen that's falls outside of the targeting for that campaign. So we need to know which shapes we know about for that. All right. So just to build this up, if we were to approach the nearest neighbor query in a naive way, we might decide, okay, let's take our point, look at all our objects, calculate the distance between each of them, put them in a list, sort it by distance, and then just take the first n entries. And that's going to give us the closest points. Obviously, this is not going to be great because we're doing a ton of work that we're just discarding if we only want n points, and we have to calculate it for 10,000 points, 5 points, 10,000. It's a lot of work that's going away. And another approach to improve this might be to cache our results so that we don't have to do these distance calculations over and over again. But that's not going to work here either because we're usually dealing with latitude-longitude pairs, floating points. We're not going to see the same point So we're going to have to do something else. So like I said earlier, we're going to arrange things in a tree structure, and we're going to try to construct it in a way that at each point we can discard a lot of our search space and try to approach an algorithm that allows us to get like log n performance like you would see in most tree search type algorithms. Again, branch and bend, that's the name. Okay, so imagine we have these set of points. These could be either points themselves, like the screens that Vistar is showing ads on, or they could be shapes in our database, like a city, New York. You could be a set of zip codes. Those are all valid objects that would live in our spatial database. So the first thing that we're going to do is we're going to segment our set of points into sets that have roughly the same amount of points in them. And for this example, we've chosen 9 buckets. So we want to just split this up into 9 roughly equal sets. And then proceed, we're going to iterate through and repeat the process in each of these boxes. So as you can see, at each step, we're kind of we're constructing smaller boxes for more dense areas. The less dense areas have large boxes, so that each area has roughly the same number of objects in it. And we're going to keep doing that. This one looks really cool. And we're going to keep repeating this until the structure is self-similar. And at the bottom, we're just going to have the objects themselves instead of their surrounding boxes. So this structure is called an R tree. It's a very common type of spatial algorithm that's useful for many different types of queries. You can think of it as a B+ tree, but extended into multidimensional space. So generally the strategy of this is that we want to group objects that are close together in the same branch of the tree. And we're going to construct minimum bounding rectangles around those groupings so that we can quickly calculate whether something is in that box or not. And the nearest neighbor, we're going to come back to this later, but is a really nice use case for this type of structure. I'm not going to go into too much detail on this, but actually constructing this is not easy. Knowing which points you put in which box is actually a pretty difficult problem. And we also want to construct it in a way that the tree is balanced, but doesn't contain lots of empty space and doesn't have overlaps, because that, once we have overlaps, we can't disregard portions of the tree as easily. So there's like a lot of research around how to do this. A nice property, though, is that we do have insertion and deletion algorithms, so we don't have to reconstruct the tree from scratch every time we want to change it. And when we're inserting, the way we know which part of the tree to insert it to is that we want to enlarge the box by the least amount. That's how that works. Okay, so we're coming back to our set of points here, and we're going to try a slightly different and maybe simpler approach. Instead of constructing these sets of points and making their bounding boxes, we're going to just pick a midpoint so that we have roughly the same number of points on each side and cut it in half. So you can see the red line is going to be the first cut, and then for each of them, repeat the process, sort of creating similar bounding boxes, but they're not boxes anymore. They're just sort of halves of these splits. And this has a different name. It's called the KD tree. So it has some limitations compared to an R tree. When you're constructing an index like this, our objects are restricted to points. We aren't able to put rectangles or more complex points in there. And we can't add or remove points to it because that immediately unbalances the tree. We don't have these bounding boxes that we can modify. We just set midpoints. However, it is faster, and you can probably conceptually imagine how you would implement this without worrying about like selecting these sets. Okay, so once we have these built, we need to query them. We're going to talk about range queries first, and just a reminder, that's when you have a rectangle and you're trying to find out what objects sit inside that rectangle. And this algorithm is going to apply to both an R tree and a KB tree. So we're going to start at the root, of course. And then, next slide. At each level, we're going to discard boxes that don't contain a protocol. And in practice, that means we're actually discarding huge chunks of the search space because most of our objects are going to be in boxes that we're not within. And the nice thing here is that we're able to use bounding boxes instead of doing a full polygon intersection, which is a fairly expensive operation, even with simplest algorithms you're going to have to use some more complex ones. So going back to our nearest neighbor, this is somewhat more complicated. Remember that this is asking us, given a point, we want to know the, say, 5 closest points in our 5 closest objects in our database to that point. And looking at this, I don't think it's immediately obvious how you would ask the structure what the answer to that question is. And something that we can do, we could maybe start with saying, okay, we'll use a radius query. We're going to construct a radius. But the problem is you don't know what radius to use because your point could be very far away from any other point in the database. Okay, so that's not going to work. But something you can sort of think about, it's not going to give us the answer immediately, but the boxes that are closest to our point are going to be more likely to contain the closest points, which is not, doesn't give us the answer, but it's like, okay, maybe we can use this, and we're going to use that combined with a priority queue to actually like solve this problem. So what we're going to do is, at each node, we're going to insert the children of the node into a priority queue by distance. So this might be the first iteration where you have several of the largest boxes in the graph in your queue. Then we're going to take off the first, or the closest box, look at its children, and then add them to the queue as well. So mix here, and we're going to keep repeating the process. Once we have a point, that point is actually guaranteed to be the closest point to our query. And the successive points, the same thing is true. And I didn't think this was immediately obvious, like why this must be the case. So it actually is kind of a nice little proof where you can make the observation that the distance to any box must be the minimum bound of the distance to any of the points of the box. So if we are looking at a point in our queue and a box is farther away, then this point must be closer to us than any of the points in the other boxes, which I thought was kind of a nice little observation. Okay, so we're going to step back again and look at one more strategy. This one is a lot simpler than what we talked about before. So this is called a quad tree. And what we're going to do is just take the globe, or in this case the US, and divide it into equal-sized rectangles. So we're going to cut it in half, and then recurse, repeat, until we get to some specified depth of the tree. As we're constructing this, we're going to look at all the objects in our current database. Our database compared to the current rectangle, and ask ourselves, does this object contain this rectangle in its entirety? And if it does, we're going to store it at that node. And we're just going to continue descending like that, and that's going to be the structure of our tree with the nodes containing all objects that are contained, that contain that rectangle. So when you want to query this is actually a very fast algorithm. You start at the top. You can do bounding box checks to determine which node of the tree to look at, and every time you look at a node, you add all the objects that contain that box to a list. You keep cursing, etc. When you get to the lowest level, you have this list that is actually all the objects that contain the point you were asking about. So this is very good for the spatial point query that we talked about earlier. And here we implemented one. This is actually like the most kind of technically interesting part of the geospatial code base of Vistar. It's a Go implementation of a quad tree that involves sort of packing these nodes into memory so that we can memory map them and use pointers to access different parts of the structure in constant time. And we use that to proxy requests to our ad serving system so that we're able to augment each request from screen with all the possible shapes that could apply for targeting. Okay, so just to wrap up, if you want to look at this some more, PostGIS is an extension of Postgres that has lots of good indexing built into it, so you don't have to implement this stuff yourself. You can just add it to your Postgres and start playing around with it. If you like really cool, dense textbooks, this one is cited everywhere and is really good. Probably I haven't looked at it. It does look really cool, and I wish I had a copy. And the Mapbox blog, which is where I got a lot of the graphics for this talk from, has lots of interesting stuff and open source JavaScript implementations of these indexes if you want to play with them. And that's it. And we're hiring. That's the site. Questions? Yeah.
Do you use PostGIS for doing this stuff?
The spatial database that I would refer to is like actually PostGIS here.
Okay.
It stores all our shapes.
Your Go plot tree thing, is that actually like open source, or is that just like
Journal not open source.
Thanks a lot. So just like hanging fruit, you know?
Well, you just got
Good answer.
anything else? Thanks.
Cool. Well, thank you all for coming out. I'll keep the doors open for a bit longer. Hang out, ask questions, do what you got. Thank you again.